Yeah, probably take something else in the class.
My diet, well, we're gonna both have maps, right? I have them now. Yeah, so I do too. The homework for me, I usually do it during the day because I have it last class.
Oh, okay.
It usually takes me about an hour and a half worth of work.
Yeah, it takes me about an hour. The last one took me about an hour.
Sometimes it takes less. Today's I haven't finished yet. I finished the second two problems, but the first one, even though it's like the easiest
Say hi.
problem to figure out, like logically to figure out.
Can you hear me?
Thank you, English. The second 35 kinematics on. Let's do on Monday.
Wait.
I'm talking about the one that's due.
Let's just turn the camera. Say hi to one person online. Hello.
Because one of them is basically like identical.
So hopefully you are having a great trip. He's actually attending cross country right now. I don't think right now. Yeah. Okay, good.
So I got most.
Okay, so if you have a question anytime, okay, just unmute your microphone, start saying something. Okay. All right. Okay, so it looks like one person online. Everybody else is in class, I hope. And then I have to warn you, today is probably important class. And then once today, if you fall asleep, you know, it's your freedom to sleep any way you want to, but this is not the place. You're paying like $100 on a minute to sleep, probably. Okay, anyways. Okay, so let's just get going. 1 o'clock. Before I close the door, I'm going to take attendance, then I'm going to close the door. It's going to be much easier. So let's just take in-class attendance. Thank you.
I didn't. I knew this, but I didn't remember until I checked the quiz page. But Dr. H uses what I like to call the Poon grading scale, because I had Dr. Poon for Calc 3, and he uses the same grading scale. And I have no other professor that I've met that uses the grading scale. But because, and I don't know why this is, I think it's because, and this is at least my theory, they acknowledge that their class is difficult the most, so they grade off of a 13 or 18-point scale rather than a 10-point scale. So technically, like, a B, you get a 76 instead of a B, if that makes sense. So rather than 10 points to a grade, it's like 13 or 14.
So I think I'm going to probably make the standard set of rules. One of them is once I close the door after I take in-class attendance, maybe I feel safe to say, sorry, please attend online. You can go to that. Open up your laptop, or log into that machine and attend on. I feel terrible to say that, but since the school demands who's sitting next to you all the time, that's why I'm taking it. It's not me doing it. Okay. All right. So, yeah, go ahead, Michael.
I have a question for you.
Go ahead.
So if we had 1 Newton on Mars and we were trying to convert it to kilograms of force, would we divide by, to convert it, would the easiest way to do it just be to divide by Mars's gravity?
Listen, conversion factor never change no matter where you go.
Okay.
So, I think, what's the conversion factor? 1 kilogram force is 9.8 Newton. Right?
Correct, yes.
It is always there.
It's always not.
It never changes.
Okay.
So think about that. But the gravity changes.
Yeah, yeah, right.
Well, that's why the kilogram force value changes.
Okay.
So on Mars, 1 kilogram of mass doesn't create 1 kilogram force because the gravity is different. If you plug into mass times gravity, it's going to have a create Newton. Then if you convert that Newton into kilogram force, it's not going to be original kilogram mass anymore.
Okay.
Only on Earth, 1 kilogram mass creates 1 kilogram force.
Oh, okay. Okay. Thank you.
Go ahead.
So specific weight changes.
Specific weight changes, yes, because it's a density times gravity. That's a specific weight.
Local gravity, right?
It's the gravity of your planet where you are.
Yeah.
So if you go to Mars, specific weight is different value.
Yeah.
But the density never change.
Yeah.
But if you multiply with the gravity, which is different value, it's going to be a different value, right? Good point. Why are you asking it now? I mean, you went through it, right?
What?
Quiz one, you went through it. I thought you mastered it. Wasn't it not true?
We mastered it on Earth.
Okay. What? It's not that unless I speak like a viceroy. Episode 1, Star Wars. Process them. Oh, take the princess to the prison. Process them. Oh, I shouldn't say that. I'm sorry. But I'm not gonna do anything without approval of saying it. Well, I'm sorry. This joke is not working anymore. I'm sorry. I stopped doing it.
No, it's a good joke. I just saw the Star Wars recently.
Oh,
So
Episode 1?
Yeah.
Oh
really
yeah.
simple.
What's the viceroy? That's me. I mean, kind of like that. I speak like that.
Similar, yeah. Very
Oh
similar.
yeah, that's right. It's supposed to be Japanese. I don't know why they choose that character. Okay. Updates. Do we have new updates? Yes, we do. Did you notice? This is announced today. It's a new update. Understanding and mastering the Bernoulli's principle. That's why today's class is so important. If you sleep it, you're not going to do this well. I guarantee. Okay, so stay awake for your own good sake. If you're still falling asleep, it's your decision. This is a free country, okay? But anyways, this is due next week, not the Monday, Wednesday. I don't want to ruin your weekends anymore. But if you don't do it before weekend hits, you keep worrying about over the weekends. Can you enjoy such a thing? I don't know. So anyways, this is due Wednesday next week, not Monday. First of all, you have to complete and figure out all by yourself solutions of quiz 0 problem 4 as usual. Problem 4 will make you feel, wait a minute, am I doing right? Because I'm solving this problem using this equation, and then, oh, Mach number 0.3 something. Oh, well, let's round it off and pretend like nothing happened. Or you have to start thinking about, do we have any alternative to this approach? So now then you're looking at quiz 4. Quiz 4 is positive, okay? So this is a real quiz. So do you actually still apply Bernoulli or not? It's your decision. Okay? Obviously, you're going to check carefully what's the Mach number here, Mach number there, in and out both. So both Mach number must be way less than 0.3. Otherwise, you're going to introduce lots of errors using Bernoulli's equation, obviously. Okay? So that's something. So please submit your work into the shared Embry-Riddle OneDrive file folder, submissions file folder before noon, Wednesday, September 29. This is a quiz4.pdf. Okay? Any question about that? Quiz 4, if you take a look at it, it looks kind of similar to quiz 0 problem 4. What is the difference? Please read through it. Okay? So do your best to apply what you learned, especially today's class. Okay? So let's just move on. We are spending several class periods going over this unit A3, and then we finally gave up. Okay, Bernoulli's equation is not good, especially for high speed, because we are completely ignoring something which needs to come into play when we try to take a look at high speed. Because high speed flow, obviously this thing happens all the time. Okay, so this is important thing. Notice, if you look at the unit mass of air, that unit mass of air creates the volume. That's called specific volume of air. Specific volume of air is no longer constant in high speed. Compressibility comes in. That's what you call compressibility of high speed aerodynamics. Expansion compression always happens. That is essentially energy transfer due to work. Okay? So you're going to introduce energy transfer due to work because the work is produced because of the high-speed flow field. That is going to change the energy level as it moves. Okay? So how can we include that kind of thing? That's the main subject. Then we introduced the first law of thermodynamics. So we are going to go back once again. Sorry. I always have to change it up. Okay. Sorry about that. Okay, so we are going to once again take a look at this equation. Delta Q plus delta W is equal to dE, first law of thermodynamics, okay? So let's remember, this is always the starting point, first law, thermodynamics, okay? First law simply says whatever the heat transfer is and whatever the work transfer is, if you combine those two, it's going to be the internal change of energy, internal energy per unit mass. This is the first law of thermodynamics, control mass form. Okay, we always go back there. And then important thing is happening, we discovered that in high speed, this is happening always. Oh yes. Compression expression is essentially the work energy transfer. It's happening because it's high speed. It just keeps going. So we are no longer ignoring that. So let's move on to that. So we incorporated this moving boundary work into the first law of thermodynamics, and then we introduced two equations, right? Two equations of first law of thermodynamics. This is still first law of thermodynamics. We just incorporated the work into the equation. So those two equations actually leads you to the definition of two different specific heats. Specific heat under the constant pressure process, specific heat under constant pressure process. In other words, pressure and volume always involved, right? So in order to determine specific heat, you have to assume one of them being constant. Otherwise, how can you figure out this component? That's the whole thing. So we spent some time trying to incorporate specific heat under two different conditions. One condition is volume constant, one condition is pressure constant. If the volume is constant, you can somehow relate amount of heat transfer with amount of internal energy, right? Okay. If it's under the constant pressure process, you can relate amount of heat transfer with change of enthalpy. Right? That's the specific heat we talked about. Two different kinds. Okay. And then, as you remember your thermodynamics days, we can model the specific heat either being completely constant or still a variable, but only depending on the temperature. One is called calorie-free perfect ideal gas, one is called thermally perfect ideal gas. You can still model, those are models of perfect gas, ideal gas. So you can relate pressure, temperature, density within the flow field because it's ideal gas. But one is much easier, one is more involved. Okay, which one do you want to do? Calorically perfect or thermally perfect? Oh, obviously, calorically perfect. Oh, you know, I'm praying that the professor is not going to pick up thermally perfect problem for the next exam because that's something indicating that the professor wants to flunk everybody. Oh, professor hates those students. He wants to flunk everybody. So let's just pick up thermally perfect model of thermodynamics. It's so easy. I'm not going to do that. Don't worry about it, yeah.
You don't hate
I'm
us.
not going to.
You don't hate us.
I don't hate you.
Yeah.
No, I'm neutral, at least at this point, you know. If you don't sleep in my lecture, I'm neutral. But it could tip toward like a negativity. I don't know. I'm not sure. Just joking. Don't take it seriously, everybody. I'm just trying to make you awake. So we came up with a few equations. If we assume calorically perfect ideal gas, obviously calorically perfect ideal gas having constant value of specific heat, either Cv or Ct, you can relate the temperature to internal energy or temperature to the enthalpy itself. Okay, so using this knowledge of calorically perfect ideal gas model, if you see a high-speed flow field where pressure here, temperature here is given, you can relate those things, knowing that specific heat value doesn't change. In other words, if you know the temperature here, I know how much internal energy do you have here. Also, I know how much enthalpy do you have here. Right here, if you know the temperature, well, I know how much energy do you have. That's something like that. It's calorically perfect ideal gas model. So you have now knowledge relating temperature to energy. What enthalpy? Okay. Okay, so far. Yeah, we did that. And then today, I'm going to, okay, let's just apply in a practical sense to the high-speed flow field of aerodynamics. Now, aerodynamic high-speed flow field, in this class, we are going to limit our applications for only external aerodynamics. You know what I mean? External aerodynamics. People casually call external aero. External flows. What is that? External. That means, well, this is airplane. You have a flow field going externally over that body. That's it.
Is it doing work? Is it doing work? As it?
Because it's high speed, yeah. If it's high speed, yes. If it's low speed, no. External flow is essentially flow over some kind of body, including airplane, automotive, some other things. But we are not going to talk about something complicated, such as flow field inside of like a jet engine. It is not external flow. There are a lot more things going on, right? You have an inlet diffuser, you go through compressor, you go through combustion chamber, you go through turbine, you go through exhaust nozzle, afterburner. That's not external. Question, go ahead. Go ahead, question. Oops, okay, it's okay. So that's external flow. So we want to make everything simple. In other words, if we look at application only for external flow, we can assume this way. If you go back one more time to the first law of thermodynamics, the equation we started. First law of thermodynamics says delta Q plus delta W is equal to dE, right? Now, of course, in high-speed aerodynamics, this is always happening. We cannot ignore it. However, if we are talking about external flow only, that means oftentimes we can ignore this term. You know what I'm talking about? This is not a combustion chamber. You are not adding any heat energy. Flow is incoming, flowing over it, flows away. That's external flow. So we can assume this is adiabatic. You are not purposely adding or taking energy through heat. That's called external flow. Okay? So, hey, if this delta Q is 0, what do you call this process in thermodynamics? No heat transfer. Adiabatic. So we are going to limit adiabatic process only because it's external aerodynamics. Okay? So do not assume this equation can be applied for casually for any high-speed flow field. If you're talking about rocket nozzle, this is not adiabatic. If you're talking about jet engine, this is not adiabatic. And even external flow field, if you create a shock wave and the flow is going across the shock wave, it's not, well, it is probably adiabatic, but it's not reversible. Oh. Reversible. What is reversible? Reversible means, what is a reversible? Anybody please tell me? Go ahead.
You can do the same process forward and backwards.
That's right. In other words, you can completely reverse the process. You can retain the same amount of energy. In other words, does anybody have reversible automobile engine? Reversible automobile engine means when you start up your crappy car, that crappy car creates huge amount of smoke puffed up. That smoke, you can scrape out everything, push back into the fuel cell, and then completely reverse and 100% efficient engine. There's no such a thing. It's a violation of second law of thermodynamics if you can do that. So that means, reversible means at least if you reverse the process, you can still maintain the same energy level. What does that really mean? That means first law of thermodynamics is always true, no matter what. That's called reversible process. Now, as you take the thermodynamics, then when you hit the second law of thermodynamics, you now realize one thing. What do you realize when you hit the second law of thermodynamics? Second law of thermodynamics tells you one thing and one thing only. Oh, first law of thermodynamics? Oh, that's a lie. Don't believe it. That's second law. Do you understand? First law of thermodynamics says energy is conserved. Second law of thermodynamics says, what are you talking about? Energy is not conserved. You're going to lose energy. What are you talking about? There's no such a thing. Unless it's reversible. How many reversible processes do you think you have in this earth? None. Sorry. Something is pretty close to reversible, but none. Somebody is knocking the door.
Sorry to disturb y'all. I left some. That's my bad. Didn't want to disturb everyone. My bad.
It's better than that. Don't say that. Okay, let's move on. So what did I say? First law of thermodynamics. Energy is conserved. Second law of thermodynamics. Basically overturn the first law. Well, you always lose your energy. What are you talking about? You are going to create something called entropy. Always some portion of the energy is completely gone. You can never reverse the process. That's second law of thermodynamics. But for a moment, let's assume that you have never heard of second law of thermodynamics. That's called reversible process. So we are going to employ that idea of, hey, everything is reversible. So we are going to maintain the same energy level, and then you are not adding or taking heat energy. In other words, heat energy transfer is zero, adiabatic process. That is essentially fairly close to a wide variety application of external flow of high speed. Make sense? So let's just say, hey, flow is still isentropic. Isentropic means adiabatic and reversible process. So even though this flow field is supersonic, you can, well, this is still close to isentropic. It is compressible, yes, it's high speed. Density changes, but do you actually lose energy? Not quite. Unless you go across the shockwave or something like that. You can say that. Okay. So be careful about that. If the flow field is isentropic, obviously you can do two things. Number one, if the flow field is isentropic, you can, of course, apply isentropic relations. This relates pressure, temperature, density. Again, isentropic flow is still ideal gas. You can relate pressure, temperature, density. But it's not the relationship P equal to rho of D. Too bad. Okay? You can still use this relationship. Well, actually, P equal to rho of D anyways, but for different locations, two locations, pressure here and pressure there, if you know density here, you can get the density here using isentropic relations, because you can assume this is isentropic flow. Go ahead.
These are two places still have to be on the same streamline.
That's right, correct. We still stick with Euler's. So that's the next page. So second thing you can do is, of course, you can apply first law of thermodynamics simplified version. What is the simplified version of first law of thermodynamics? This is it. Delta W is equal to dE. This is the simplified first law of thermodynamics. Whatever the work energy transfer because of compression expansion process is going to be 100% converted into the internal energy change, so that the temperature change, if you measure such a thing, you can determine the compressibility. If you have a compressibility, you have a high change of temperature between two locations, even though you are not heating up or anything. Does it make sense? Okay, so let's move on. So now we are going to, let's just derive energy equation here, okay? All right, so energy equation. Let me just catch up my cheat sheet. Energy equation. Okay, here we go. So energy equation here. Okay, so starting point is first law of thermodynamics. Let's just take a look at it. So first law of thermodynamics, I'm going to pick up the first law of thermodynamics in terms of enthalpy. Do you remember this equation? Okay. Now, this equation relates the heat energy transfer to the change of enthalpy and VDP. Okay. Now, if this is adiabatic, delta Q is 0, adiabatic, because one of the conditions for isentropic flow is adiabatic. This equation now becomes this. So now I pick up the equation 1. Equation 1 says dH is equal to V dP. Okay. This is equation 1. This is nothing but just the first law of thermodynamics. Okay. We can use first law because this is isentropic flow. First law still holds. We purposefully ignore the second law of thermodynamics, assuming this is a reversible process. Energy level doesn't change between two locations. Energy stays constant. Okay. Anyways, so we want to combine this with something else. Guess what do you want to combine this with? Huh? Oh, remember, when we get the Bernoulli, where did we begin?
Oh, energy, you need kinetic energy.
No, when we got the Bernoulli's equation,
Conservation of linear momentum.
Euler's equation, here we go. So Bernoulli's equation, you know, is coming from Euler's equation with a condition density constant. Okay, let's just go back to Euler's once again. What is the Euler's equation? On Euler's equation, as we know, this is Euler's equation is dP is equal to minus rho b dV. Do you remember this Euler's equation? This is along a given streamline. Do you remember that? This is Euler's equation. So if you pick up this Euler's equation and assume this density is constant along the given streamline, you get Bernoulli. But now we know we cannot assume such a thing. This is high speed. Okay? So density might be different value. However, we can actually apply instead this equation, first law of thermodynamics, because this is still isentropic. Can you combine equation 1 to Euler? What do you think?
Yes.
What do you think?
You have a DP.
You can plug in, right? Go ahead.
Is you have it negative rho? Is that v for
This is
velocity?
velocity.
And then
Velocity.
velocity.
This is not the velocity. What's this?
Specific volume.
Specific volume. What is specific volume?
Inverse of rho.
Inverse of this.
Oh, okay.
Okay.
Super bad.
So you're getting it. So this is the equation 2. Let's combine equation 1 and 2.
So is it gonna be
1 and 2 combined. Let's just see it, okay? So you're going to plug in dP back into here. So dH is equal to lowercase b. dP is minus rho b dV. Those are velocities. This is a specific volume. This is inverse of density. What do you have here?
DTV.
This
Minus
is
VdV.
negative b dV, right? Oh, okay. Can we integrate this? Oh, yes. Let's integrate. So you are going to pick up the streamline. This is a location 1, location 2. Along this given streamline, you can integrate this equation. Integral between location 1 is h1, h2, dh is equal to negative integral b1 to b2 b dv. This actually gives you change of enthalpy between location 1 and 2. h2 minus h1 is equal to negative b2 square over 2 minus B1 square over 2. This is going to get you relationship between 1 and 2 saying H1 plus B1 square over 2 is equal to H2 plus B2 square over 2. This really means that simplified H plus 1/2 B squared is equal to constant. Oh, I got the algebraic equation. Kinda, well, looks kinda like Bernoulli. This is called energy equation. Okay? Oh, this is algebraic form. Cool. So suppose if I have a value of h and value of velocity, you can plug in and get the value out. And then if this is ideal gas, calorically perfect, okay? You can say H is equal to CPT, right? So you can say CPT1 plus B1 square over 2 is equal to CPT2 plus B2 square over 2. That actually simplified CPT plus B square over 2 is constant. Of course, this constant is along a given streamline. Go ahead, Michael.
Don't you mean thermally perfect? Instead of
No, caloric, well, thermally perfect is dH is equal to Cp as a function of still temperature.
that's what I'm
Yeah.
confused. Thank you. Yeah.
This is thermally perfect. You don't want to deal with it. This is calorically perfect. It's algebraic. Yeah, go ahead.
So the energy equation, that's the specific energy, isn't it?
Specific
Because-
energy per unit mass. That's right.
Yeah.
Correct. You're right. Energy equation. Oh, this is the equation I wanted to have. Now I can apply this equation for more than 0.3 Mach number because density can be a variable. However, what's the condition? Still, this is a steady flow. Implicit, no body force because it's coming from Euler. And then it's coming from first law of thermodynamics. So this must be isentropic. And also this is perfect gas, calorically perfect ideal gas. If so, you can use this equation instead of Bernoulli's for high speeds. Okay? So next page, let's just apply. Take a look at it. Go ahead.
He says steady, no body force.
That's Euler.
Is it-
That's Euler. You know Euler, do you?
Yeah, I know.
So
Steady,
that's
no
the
body
that's the condition for Euler.
Yeah, well, and then it's isotropic.
Isentropic is coming from first law of thermodynamics.
Okay.
And then calorically perfect ideal gas is also added. So you need to know all of those conditions because those are limitations for this equation. Okay. So this equation still comes with limitations, but one of the limitations is all gone. What is it? Less than 0.3 Mach number. So you can apply this equation for more than 0.3 Mach number. Okay. So let's just take a look at next page. A high-speed business jet aircraft. At this moment, you kiss goodbye to Bernoulli, right? High-speed business jet aircraft. Oh, let's apply Bernoulli's equation. Go ahead, do that. People laugh at you. Of course, you don't do that. Okay. At this moment, this is not less than 0.3 Mach number anymore. Sorry about that. So a high-speed business jet aircraft is flying at the 10-kilometer altitude with 750 kilometers per hour. This is way more than 0.3 Mach number case, of course. Okay. The temperature and pressure at a point on the wing is minus 45 degrees and 2.8 times 10 to the 4 Newton per meter squared. This is Pascal. Those are, well, yeah, okay. What is the velocity at that point? And then if this is an exam problem, I'm not going to, of course, give you this kind of hint. This hint will be gone if this is a final exam problem. Okay? And then if you casually pick up in Bernoulli and apply, you get 0. Of course. So be careful. So this is a much nicer class example problem, not the final exam. So what do you do? Well, there's a data given. Okay, so now I want to answer your question, Dan. Okay, you said, okay, so how much can we assume calorically perfect? In other words, what is the temperature range and all that? Okay, let's just take a close look. So we want to take a look at this property table, specific heat, CP, right? Let's just zoom in a little bit. This is a specific heat. Obviously, this is just a pure function of temperature. It doesn't depend on pressure, only depends on temperature. Now take a look at it. Looks like, in the range of this temperature, it looks like the value is about 1.005 to 1.009. If I'm very strict, I can only choose this range of temperature, which is minus 50 to about 40 or 50-ish temperature zone. This is 1.005. This is kilojoule, by the way. So this is 1005 joule per kilogram K, which doesn't change much in this range of temperature. This is called calorically perfect ideal gas model because it's constant in this room temperature range. However, if you go for higher temperature, well, it is going to kind of start changing to the higher value. So this is still somewhat perfect, but it's no longer constant. Okay? So that's the difference between calorically perfect and somewhat perfect ideal gas model. So you have to switch back and forth. Obviously, if you keep using constant value of CP in higher temperature zone, you are going to introduce some errors. Okay. So how much error is tolerable? That's the question. So anyway, so let's assume this, what's the temperature? Well, temperature is minus 45, okay. So in this temperature range, let's assume this is calorically perfect. So let's just pick up CP value, 1005. Okay, Joshua, go ahead.
I was just wondering, is this table we have here the standard values, or is there another table that we will refer to as standard values?
Great question. In other words, this property of air is coming from standard sea level pressure. Now, isn't this 10 kilometer altitude? Can we use still the standard sea level value? Yeah. In terms of CP, yes, because CP doesn't depend on the pressure, only temperature. Like I said, CP is a function of temperature, only, not the pressure. That's a great question, actually. So that's why we can still use this in terms of specific heat values, of course. If you start picking up other things, of course, you have to go to 10 kilometer altitude values. But specific heat doesn't depend on pressure, only on temperature. Okay, so you can still use at least this data set. Okay. All right. So first of all, what is the first step to solve this problem? So this is 10 kilometer altitude. Okay. So, what is the speed of sound?
43 meters a second.
At 10 kilometer. Speed of sound, you have to compute gamma t. So you have to basically pick up the standard value of temperature at 10 kilometer, looking up your property table, just plug it in. Speed of sound is actually 299.5 meter per second. Speed of sound is a function of temperature. So you have to pick up the 10 kilometer standard value of temperature to determine the speed of sound of 10 kilometer. That's the first step. Go ahead.
Does density have any play in?
Density has nothing to do with speed of sound. Actually, have something to do, but at least we can use this equation. Okay. Yeah, so we're gonna find out more details about speed of sound equation, but yeah. For a moment, let's just ignore the density effect. You only worry about temperature when you figure out speed of sound at this moment. Okay. So Mach number is, of course, velocity over a, speed of sound. So you are given 700 kilometer per hour, 750 kilometer per hour. Let's just convert it to meter per second. So this is 1,000 meter over 1 kilometer. And 1 hour, 3,600 seconds. Divided by 299.5 meter per second. Actually, if you compute this conversion process, you actually get 208.333, okay, meter per second. So 208.333 divided by 299.5 will get you the speed of, this is Mach number 0.7. Whoa, you go like, whoa. This is more than 0.3. I'm doomed because the only equation I know is Bernoulli. So no, I cannot use Bernoulli. So what?
Apply the code for the perfect. The energy equation.
Energy equation. So let's say, okay. So let's say, okay. So let's say this is an airplane. Airplane flying in high speed. Okay. Roughly speaking, this is airplane, and then you're going to probably assume, hey, this kind of streamline is involved. I don't know. And then let's say this is location 1, and let's say this is location 2. Location 2 is something you are interested, okay? Because location 1 is a free stream, infinity, okay? Now at this point, do we know the temperature T infinity? T infinity is a standard 10-kilometer temperature. You can look it up, 223.3 Kelvin, okay? Which is T1. What is CP? Ooh. And this is B infinity. B infinity is how fast you're flying. This is a free stream, right? You found out this is 208.333 meter per second, right? This is B1 right here. This is a free stream right here. This is actually, by the way, in practical sense, how fast your airplane is moving with non-moving air, right? You remember that early bird, we switched the frame using Reynolds transform. Airplane is not moving, but the air is moving. Okay, that's called free stream. So free stream condition here is a standard atmospheric at the 10-kilometer, which is a 223.3 Kelvin, and then this is the 208.333 meter per second. So this is how fast the airplane is actually moving. That's the free stream condition. Right here, okay, what is the velocity here? That's what I want to know. Do we know the temperature? I don't know. Can we get a temperature information from there?
Yes.
Temperature is given. Oh, minus 45. Minus 45 P2. No, temperature, sorry. T2 is minus 45. Oh, temperature information is given. So this is going to be in Kelvin minus 45 plus 273 Kelvin. Oh, that's the temperature right here, 0.2. So out of this information temperature, can I get velocity V2? Can I? Any idea of what equation you want to pick and use? Go ahead.
Energy balance.
Energy equation, that's right. Energy equation, let's just pick up energy equation. So energy equation basically says, oh, let's assume calorically perfect ideal gas. Because temperature range is minus 45. So calorically perfect ideal gas says Cp T1 plus B1 squared over 2 is equal to Cp T2 plus B2 squared over 2. So from here, B2 is equal to square root B1 squared plus 2 times Cp. T1 minus T2. 4. Let's just plug in. B1 is what? B1 is 208. Okay, 208.333 meter per second square plus 2 times Cp value. You're gonna pick it up from the table given. What does that say? 1005, isn't it?
1005.
1005 joule kilogram K Kelvin. Okay. And temperature is T1, 223.3 Kelvin. Subtract, T2 is minus 45 plus 273 Kelvin, right? Now if you compute this through, you're gonna get D2, which is 184.27 meter per second. Okay. You have to double check by using the temperature value given T2. Temperature T2 will give you the speed of sound A2. Make sure divide 184.27 divided by that speed of sound at location 2 to come up with a Mach number. Mach number should be 0.6-ish. So both more than 0.3 in this case. Go ahead, Mike.
If it's not more than 0.3, you have a problem.
I think you shouldn't, because one of them is exceeding 0.3, so you know that the Bernoulli is casually cannot be used for this case.
Right.
Right?
Yes.
Yeah, so I guess, but the double check to see, so what was the actual Mach number at the exit? Well, still more than 0.3, but 0.6-ish, still subsonic, not the supersonic or crazy speed. So we are okay, reasonable range. Go ahead.
If we do have a problem that either starts above 0.3 and then goes below, or starts below and then goes above, how should we approach it?
You have to double check both cases. In other words, the only case that you can still use the Bernoulli is both less than 0.3. That's the only case you can use Bernoulli.
I know, but like if we were given a problem where we double check the speeds before and after, like is there a different or is there a different equation we use for going between?
No.
So you can't do anything if you're going between?
Let me answer that question going for a little bit more depth. Do you have any question more? Go ahead. Let's not ask those kind of specifics. Let's just go back to the little bit more like a detailed conceptual idea why this is working, why not the other one working. Question, guys?
I was just going to make a comment that one way we can tell that the Mach number that we're ending up with is always going to be above 0.3 is the fact that we have our initial velocity of 208 squared in the square root. So it's always going to at least be greater than that.
So basically, you have a variety of cases. Some of the cases that you have starting with less than 0.3 Mach number at the free stream, however, because you create a very sharp acceleration surface, that may go exceed 0.3 at certain location. If that kind of thing happens, how can you analyze? Of course, the only tool you can use for that case is energy balance. You know why? Because typically low speed wind tunnel, I don't want to do this today in 5 minutes because this is so important. I don't want to miss this. So coming back on Monday, let's just take a look at the details of what the earning bird is trying to say. So I want to revisit once again on Monday because I haven't finished the last page. Okay, sorry about that. So this is the last page. So you guys have a question based on the motivation that, hey, I know I have to do quiz 4. So Professor, I want you to answer my question. If the quiz 4 is the case that one end is less than 0.3, the other end is more than 0.3, what is the right option? Is it Bernoulli or energy? It's energy, yeah. But here's the important thing. The important thing is why? And then why people actually use Bernoulli in low speed wind tunnel. If energy equation is better than Bernoulli, why don't you pick up energy all the time? Avoid the complication, and you don't have to check Mach number. That is my question to you. Do you have an answer for that? Go ahead.
I believe it's due to the compressibility.
Yes,
Like
it is compressibility, but it's not the answer for why. Right?
Is it because you can get more details from Bernoulli's equation, such as pressure and static?
More details in those speeds. Yeah, you're kind of close. Go ahead.
You can measure your like free stream temperature, but it's hard to measure your like T2 temperature, like if you're testing on like a wing or something.
So that means how much accurate information will be available in low speed versus high speed. In other words, in low speed wind tunnel, do you think you can measure very accurate temperature change from one location to the other location to the other location? There's no way you can do such a thing because the change is so insignificant. No matter how accuracy you want to have, it looks like it's all the same temperature. So you have to rely heavily on pressure information. That's why you're using manometer in low speed wind tunnel, right? Now, high speed flow, think about that. If you have significant enough temperature change, because this is really high speed, and then if you get such an information for the flow field, obviously, you should go for energy equation. But it is rare for low speed testing to get such an information. Actually, temperature is always the same. That's what the people say. So in a practical sense, that's the reason why low speed Bernoulli is something called pressure velocity coupling. You are given pressure information, figure out the velocity out of it. Pressure velocity coupling. Now, high speed energy equation, on contrary, that is temperature velocity coupling. If you are given accurate enough temperature variation within the flow field, because it's high speed, you can relate to the velocity. Temperature velocity coupling versus pressure velocity coupling. Low speed and high speed. Where's the boundary? About 0.3 Mach number. Okay, that's where the isentropic assumption comes into play. Okay, so we're gonna finish up on Monday. So I knew it because I'm probably not gonna be able to finish today's. So that's why I made it due Wednesday. So quiz 4 is coming up, which is due Wednesday. So we're gonna finish up on Monday. We're gonna go back to, once again, the Bernoulli equation. Take a look at one more look at the Bernoulli equation. Go ahead, Michael.
Is there any way
Yeah.
to, you do your first check, you look at the initial velocity,
Yeah.
7.3, but is there any way to check the second velocity?
You have to go through the analysis, and then you find out the temperature at the exit. That's actually going to give you speed of sound information.
Right.
Then you can determine microphone.
Okay.
So you have to go through the analysis to check that problem. That's
Okay, and
what.
then if it's wrong, then you go through the second.
That's right.
Okay.
Yeah. All right. Have a wonderful weekend. See you guys back on Monday.